And welcome to Ontology Talk. I'm Adam Pease, and today we're honored to have Dr. Josef Urban with us. Dr. Urban is a researcher at the Czech Institute of Informatics, Robotics, and Cybernetics, and he's been heading an EU project called AI for Reason. Prior to that, he was a postdoc researcher in the Netherlands and an assistant professor at Charles University in Prague, and a Marie Curie Fellow at the Department of Computer Science at the University of Miami. Welcome, Josef.
Hi, Adam. Good to see you.
Yeah, great to have you here. So I thought we would get started maybe just talking about this project that you've finished. It's a really major project. I mean, a 5-year project with lots of participants. And as I understand it, it was largely about combining theorem proving and machine learning. So very groundbreaking stuff. Can you tell me a bit about the project goals and accomplishments?
Yep. So the project is called AI for Reason. It started in 2015 in September. It's a project called ERC Consolidator. So ERC stands for European Research Council. So these are big, relatively big individual projects awarded by this sort of European funding agency. And it's sort of a touted as high risk, high value project. So we are always supposed to promise something, some sort of moonshot, and then convince them that you have a decent chance to do it, and then work hard on trying to do it. So in this case, it was about combining machine learning and automated reasoning. So I basically wanted to see how far we can push the power of automated reasoning, and in particular automated theorem proving, by learning from large mathematical corpora, like imagine something like mathematical textbooks, basically. So the basic argument is that humans are good in proving hard theorems like Fermat's last theorem or whatever classification of finite simple groups, like all these great achievements that mathematicians are capable of, because they study and they think and they somehow combine trying to solve problems with learning from their attempts, like both the successful and the unsuccessful ones. And like what I have been trying to do basically since my master's or PhD work was to somehow emulate this combination of learning and reasoning on computers. So that's like the main page. So we took some relatively big mathematical corpora, which would be like an approximation of the mathematical textbooks, and we took various automated theorem provers, like eProver, for example, or simpler provers like LeanCode, like the connection system, and we equipped them with internal machine learning guidance. So that was like the main thrust of the project, where we did probably the biggest breakthroughs. So for example, in like 2 years ago, we finally made it work with eProver. So we equipped eProver internally with a guidance using gradient boosted trees, which is like fast but state-of-the-art machine learning system, and trained it on, like, let's say 100,000 previous proofs, and ran it in several proving and learning loops. Like as it proves, it sort of generates data, and then you learn, train the guidance on them, and then you prove again and you prove more. And in that mode, it gave us something like a 70% improvement from the original good eProver strategy, which was solving something like 15,000 problems over Mizar. In the like 6th iteration, it could solve 70% more, something like 25,000. So that was probably the biggest breakthrough, and that probably shows what we are doing. We, like in the final evaluation that we finished just like 1 month ago, we basically increase the overall power of like various portfolios and combinations of provers over this large MESA library, like from 40% of proved theorems to something like 60% of proved theorems. So the sort of overall outcome of the project is like almost 50% improvement of the power of automated theorem proving over such a large corpus where you are allowed to sort of do these things, to sort of train from previous provers.
Wow, fantastic. So, maybe I should just actually take a step back in case we've got viewers that are watching that maybe are not intimately familiar with formal mathematics or even with theorem proving. Let me try to give you my very layman's summary of what the objectives here are. So I take it that if viewers have had high school geometry, right? They were doing proofs in high school geometry, maybe proving that one triangle is the same because the angle and side are the same. Hopefully that rings a bell to people. But instead of doing a little proof of 7 steps, mathematicians, like if they're proving a big challenge in mathematics, something like Fermat's last theorem, I think that took like hundreds of pages of mathematical steps, each one provably true from the next, but going gradually from the question that's being asked to the answer, using all the things that we know to be true about math. And if we can get machines to help with this process, we can hopefully advance mathematics and have more answers to more hard problems in math, because then the human mathematician has a good assistant. And it sounds to me like what you're doing with the machine learning is, instead of having sort of the worst case theorem prover that just does a blind search, applying any kind of truth in mathematics it can think of, well, they're better than that, right? They have heuristics, but you've sort of improved those heuristics, so now you're getting a lot more and faster answers out of it.
Yeah, exactly. So you sort of nailed it. So indeed, like we do not have a fully formal computer verified proof of the Fermat's last theorem. That's sort of the last missing achievement or a milestone in the world of formalization. But we have other great achievements, like Tom Hales, who is a great mathematician working at the University of Pittsburgh, has proved in late 90s with his student the Kepler's conjecture, which has been an open conjecture about the optimal packing of balls in the space. And
oh yeah, I remember reading about that. Right, yeah. So it's like how you've got a big box and you've got a number of spheres. I guess I think of different sizes that you can pack into
of the same size.
The same size that you can pack into the box, and if you could have a robot laboriously arrange them, how many could you fit in the best possible way?
So there are several packings that have the optimal density, but it wasn't clear whether there isn't a better packing. So he used sort of computers to help him to get the proof. Like he did a lot of decent math and a lot of decent like programming to get the proof. And then when he did it, the mathematicians couldn't review the proof. So that was quite interesting situation, because you got the best people in the field meeting for, I don't know, 4 or 5 years in a seminar where they were reviewing the proof. And in the end, they said something like, like we have checked a lot of the proof, but it's so big that we cannot really say whether this is a proof or not. And Tom really saw this as a bug, and he decided to prove it formally, to replace the human referees with proof assistants. And it took him a lot of, so the formal verification finished officially, I think, in 2014, and it involved like 20 to 30 person years. But indeed, like it's now finished, so it's like formally the proof is verified. The Kepler conjecture has been certified by these very secure proof assistants. And if you look at the sheer size of the proof, So we have actually done various experiments with this full proof of the Kepler, formal proof of the Kepler conjecture. It's billions of inference steps. So it's really it's really something which the normal mathematicians never really encounter, like expanding your human level proof to these bottom level modus ponens style inferences and counting how many are there. So it's really billions for a proof like this.
We'll pause our conversation there and return in our next segment for part 2 of my interview with Dr. Josef Urban.